Okay, so this next one is exercise 59, and here we have a positive integer n which is odd and greater than 1, and we are viewing the dihedral group Dn as a group of permutations of a regular n-gon, a regular n-sided polygon whose consecutive vertices have been labeled like this. Now we have already seen this being done in some of the previous exercises. So we already know what this is. It makes us correspond elements in Dn with permutations of a regular n-gon. Precisely this means permutation of the vertices of a regular n-sided polygon. Now under this correspondence, then every element in Dn will correspond to a permutation. Specifically the rotations in Dn. We know there are two types of elements in Dn, rotations and reflections. All the rotations correspond to even permutations. In other words, explain why the rotation subgroup of Dn is a subgroup of An. We know that rotations in Dn, if you take all of them together, they form a subgroup of Dn, and not just any subgroup, a cyclic subgroup. In fact, it's the cyclic subgroup generated by this rotation. The rotation of the n-gon about its center through an angle 360 degrees divided by n, or 2 pi by n radians. This rotation alone generates all the other rotations, in this sense that all the rotations are in fact integral powers of this rotation, so that the rotations form a cyclic subgroup of Dn. Now each such rotation corresponds to a permutation according to this setup. Those permutations must be even. That's what we have to show, because this is a subgroup of An. So let's see the solution. You can see that because all the rotations are after all expressible in terms of this rotation only, it's enough to look at the permutation to which this rotation corresponds, and then from that permutation we can see the other permutations which correspond to the other rotations. So the solution goes like this. Viewing Dn as mentioned, the rotation R360 divided by n in Dn corresponds to the n cycle. This specific n cycle, because consecutive vertices of our n-gon have been labeled like this. You understand what is going on here. Say you're in, okay, again see, I have this bad habit of drawing geometric figures like graphs. So if I label the consecutive vertices like this, where I have chosen the clockwise sense of labeling the vertices, you can choose the counterclockwise sense also. It will not make any difference basically. So this rotation will, we already know, if you do it about the central point of the polygon, then this rotation will take 1 to 2. Because we have labeled the vertices like this, let us also assume that this rotation is clockwise rotation from our point of view. So it will move 1 to 2, 2 to 3, 3 to 4 and so on, and ultimately n to 1, and that in fact represents this function or this permutation, this n cycle. Okay, so that is the correspondence. You need not draw this figure here, I am just simply showing it for our understanding. Since the rotations in Dn are this, the ith power of this element, where I varies over the set of integers. In fact, you need not take all integer values. It's enough to only take n values starting from 0 and ending with n minus 1. But that is not something we are concerned about. We are just using the fact that every rotation is in fact an integral power of R360 by n. That's it. So the corresponding permutations corresponding to all these rotations are the corresponding powers of this n cycle. Why is that so? Because this correspondence is not simply a correspondence between elements in Dn and permutations, but it also respects the binary operations, so that if R360 by n is corresponding to this, then this power of R360 by n will correspond to the corresponding power of this thing to which R360 by n corresponds. Now, since n is odd, it's given that n is odd, this n cycle is an even permutation. In fact, we know much more. We know more than this, that not only is this true, but the converse is also true. In fact, this is an even permutation if and only if n is odd. Now, because the n cycle is even, any integral power of it is also even. That's because an is a subgroup of Sn. So you get one element, that is this element in an, any integral power of that element will also be in an by closure property. Closure property and existence of inverses. Even permutation. Hence, all these elements which correspond to each one of them corresponds to some rotation from Dn. All of them belong to An. Thus, the rotation subgroup of Dn is a subgroup of An. This last sentence, which is also there in the exercise, it seems like the sentence is actually not true, and in fact, strictly speaking, it is not, because the elements in Dn are geometric transformations that you apply on a geometric figure, namely the n-sided regular polygon, whereas the elements in An are permutations. They are not exactly the same thing. However, under the correspondence that we are considering between these two types of elements, the rotation subgroup, that is your cyclic subgroup, is a subgroup of An. If you want to make this statement more precise, then you should say like this: the rotation subgroup of Dn is having a copy of it inside A. That is, there is a subgroup of An which looks exactly like the rotation group in every respect. Group theoretically, there is no distinction between the rotation subgroup of Dn, that is that R360 by n, the cyclic subgroup generated by that, and the subgroup that you will get here, consisting of these folks. And this identification that they are practically the same thing, that can only be made precise when we have the notion of an isomorphism between two groups, which we do not have yet. Okay, so although it seems like this statement is not true, it is true in that sense, and here the word is has been used in a loose sense, not literal is. Anyway, this is our solution. So let us now see the next one. Let n be an integer greater than 1. Like before, but now it's not mentioned that n is odd or even, n can be anything. The only thing is that it should be greater than 1. Again, viewing Dn as a group of permutations of a regular n-gon with consecutive vertices labeled as this. Determine for which in all the permutations corresponding to the reflections in Dn are even permutations. So this time again we are having almost the same setup. Again we are having n, but n is not necessarily odd. N is still greater than 1, and viewing Dn as a group of permutations just like before of a regular n-sided polygon whose consecutive vertices have been labeled like this. This time we are concentrating on the reflections in Dn. Rotations we have already seen. Now the reflections in Dn, we have to find those n for which all the reflections will correspond to even permutations. That means will correspond to elements in A, and hint is given. Consider the 4 cases Consider the 4 cases for n mod 4. That means depending on what the remainder is when you divide n by 4, you will of course have 4 cases. So we have been asked to, we have been advised to consider those 4 cases separately. Now I am going to write an incomplete solution. I will consider only one of those 4 cases, namely the one where n mod 4 is 0. So that means now our n is a positive integer divisible by 4, and here I am going to consider the first 2 values of n, namely n equal to 4 and n equal to 8. So we are actually going to draw a regular a square and a regular 8-gun and see what we can get from there. So I will just simply, so it's actually, I should not have written solution, but you can understand because this is how we start things. It's more like a hint to an actual solution. So if you consider a square, say, So this is your square, which may not be perfect geometrically, but that's enough for us, whose consecutive vertices have been leveled like this. Now we are going to consider reflections. Now for the square, we know that there are 4 reflections, but also from the general structure of the group D2, we know that just like the rotations, the reflections also can be, all of them can be expressed in terms of only one reflection, and that reflection is either this one, that is the reflection of about this diagonal, or about this diagonal. So without loss of generality, we are considering this diagonal, and let S be the reflection about this diagonal. Let S be the reflection of the square about the diagonal 1, 3. It looks like 13, but in this context it's 1, 3. These are names of vertices, not simple numbers. Then all the reflections of the square. Okay, wait, I think okay. Dn has 2n elements, so that means it will have 8. D4 will have 8. Yeah, it's okay. I got confused between this n and 2n. So that means we are in D4 right now. Fine. So then all the reflections of the square, or all the reflections, we can, instead of writing like this, in D4 we can write are these. One of them, of course, is just simply S. Another one is this 360 divided by 4, that means R90 S. And this is how all the reflections look in DL. This we know from the in D4, this we know from the structure of D4. And R90, if you perform 4 times, it's the same as doing nothing. That is R0, the identity element of your group. Okay. Now, S corresponds to what permutation? If you really think of the physical, the geometric operation, 1 and 3 will remain in their places, but 2 and 4 will interchange their places. That means the corresponding permutation is the 2 cycle 2, 4. S corresponds to permutation 2, 4. So and correspondingly we can now write the other permutations also which correspond to all these reflections. So all the reflections in D4 correspond to these. For the first one I did not write the 4 cycle because it's just simply S. For this one then and now is n equal to 4 a value of n for which all these are even permutations? That's what we have been asked, right? We have to find precisely those values of n for which these things corresponding to the reflections are all in an. Is that the case? Clearly that's not the case. That's because this itself is an odd permutation. This thing is not in A4. So that means n equal to 4 is not the type of value of n that we are looking for. Let us go to the next step, n equal to 8, and let us in fact for that one also draw the figure and follow the procedure similarly. But because we have seen this once in detail for n equal to 4, we can afford to be a little sketchy for n equal to 8. For n equal to 8, as the number of sides increases, the accuracy of my drawing will decrease correspondingly. Geometric accuracy. Okay, so this very roughly represents the regular 8-gun, an octagon. Now here, that reflection which will generate the others is the one about this axis. The longest possible diagonal in your n-gun, and let S be the reflection about about the do we call these things diagonal? And I'm not so sure. 1 5. Okay, this corresponds to the permutation this first. Okay, so now if you reflect your figure about this line, then you can clearly see, because it's a regular polygon, 2 and 8 will interchange their places, 3 and 7 will do such, and 4 and 6. So this corresponds to this permutation. 2 8, then 3 7, then 4 6. It's not necessary to write them in any particular order, because you can change the order. The permutation will not change. They are disjoint cycles, so they commute amongst themselves. But note that just like the previous S, this time you can call this also some S, is odd, is an odd permutation, simply because it's the product of 3 transpositions, 3 2 cycles, and the number 3 is odd. There, when n was 4, that number was 1. So this itself does not belong to A8. So you don't even have to look at the other reflections in D8 to see whether they belong to A8. One of them has failed, so that means for our purposes it will not work. Since, or we can write like this, note that this is odd. But what about the general case? What will happen if you have just n? N is not 4 or 8 or any such specific value, n is just n. But because we are considering the case where n mod 4 is 0, so our n now looks like this: 4k for sun, positive integer k. And if you so here you will have to consider a regular n gun, a regular 4k gun, and in that figure also, just like the cases n equal to 4 and n equal to 8, you will find 2 vertices, so that if you join them by a line, that will be the longest diagonal in that figure. So do you see what is happening in all these things? When we had n equal to 4, we had to ignore these 2 vertices through which the diagonal is passing, and which is in fact the axis about which we are reflecting the figure. So if you just ignore them, the rest are 2 and 4, and they interchange their places. If you ignore 1 and 5 here, the rest are 2 and 8, 3 and 7 and 4 and 6, and this number seems to be odd. I mean, what number I am talking about is the number of vertices lying on either side of the diagonal. Here that number is 1, 1 on this side, 1 on this side. here the number is 3, 1, 2, 3 on this side, 1, 2, 3 on the other side. Is that the case in general? Let's see. Here in this case, if you neglect two vertices through which you have drawn that diagonal, then the rest of the vertices are n minus 2 in number. That means 4k minus 2 in number. Okay. Now if you here that 4k minus 2 in this case is 2, 1, 2. In this case that is 6, 1, 2, 3, 4, 5, 6. That is 8 minus 2 is 6 and 4 minus 2 is 2. So that number is this number. What you do then, you divide it by 2 to count how many vertices are lying on one side of the diagonal. So if you do that, you are getting this number. That is 2k minus 1. And from the look of this number, you can immediately see that it is odd. It does not matter what k is, what positive integer k is. For any positive integer integral value of k, 2k minus 1 is odd because of its structure, the structure of the number. And we can of course hence see the same thing here. The number is 1, it is odd. Here the number is 3, that is odd. And because of this oddness, the cycles that you will get, there we have got one cycle, here we are getting 3. Here we will get for this one, I mean if you write the permutation to which this reflection in this general case corresponds, that permutation will be a product of 2k minus 1 number of 2 cycles. Because that number is odd, that permutation is an odd permutation and it does not belong to A4k, AN. So that means when your n mod 4 is 0, then all the reflections are not in AN. Let me just write that conclusion. When n mod 4 is 0, all the reflections in Dn do not correspond to even permutations. So that means multiples of 4 are ruled out. They are not the type of n we are looking for. Then you have to look at these other cases. Similarly, keeping in mind that in each case you are actually looking for the situation that all the reflections are corresponding to even permutations. Whether that is true or not, that you have to see. And if you come across one such n, then that n will be the sought after n. Because we have been asked to look at these 4 cases, so it's likely that one of these cases will be a case in which if your n is lying, then for that n, all the reflections in Dn will correspond to even permutations. Now you can of course ask me the question, fine, but then why did we write all the reflections in terms of that single reflection? Because here one reflection is failing. That may not be the case for the others. Maybe one among these is our sought after case. So there you will need in fact all the reflections to see that they are actually corresponding to even permutations. And we need that form also, namely your rotation to the power I times reflection. This is how a general reflection looks like. And one more thing that I must mention, what will you do if your actual n is odd? If your n is odd, you will not get such two vertices through which a longest diagonal passes. Let's take the simplest case. If you say consider an equilateral triangle, that means here n is 3, and so this value of n lies in this last case. Here the axis of reflection will never pass through two vertices. Instead, they pass through one vertex and become the perpendicular bisector of the other vertex. Okay, so and this type of things, this type of reflections will generate all the reflections. If you go to next higher case, say you take your n to be 5, that means n being odd, you look at the next case, that is if you are looking at a regular pentagon. Then here that axis will look like this. Here an entirely different thing will happen. You can almost see, if you reflect this figure, for example, that corresponds to a permutation which is a one cycle, which interchanges these two vertices. The similar thing if you do here, it's a product of I said one cycle, one two cycle, a single two cycle. For this case, here it is a product of two cycles. So here it's just like the 4K case. Here, however, it is even. It's a product of two cycles. And this case, n equal to 3, and this one n equal to 5, of course they belong to different congruence classes. N equal to 3 belongs to this case, whereas n equal to 5 belongs to this case. Okay, so accordingly these other cases I am asking you to go through and see what you find, because I have not actually gone through them, and I don't know what the ultimate answer is. So I ask you to do this for me and let me know. So this is an incomplete, I should not say solution, but rather a hint to an actual solution, because in the 4K case also I haven't written things down formally. So that part also you have to do. Instead, let's just see the next one. You just have to keep in mind that when n is even, when the number of vertices of your regular n-gon is even, then you will find two vertices which are the farthest in your n-gon, and the reflection above the axis which passes through those two vertices is a reflection using which you can generate the other reflections. Whereas when your n is odd, whether it is like this or like this, that is belonging to these two cases, then that axis through which if you do a reflection, that will generate the other reflections in that specific way, r to the power I times s, where r is rotation and s is that reflection. Then that axis has to pass through any one vertex, and it will have to be the perpendicular bisector to the vertex which lies directly opposite to that vertex. Okay, I mean this side, the side opposite to that vertex, that you have to consider. Show that, yeah, this one is rather easy. You may be hearing some rumbling noises in the background. It's because of thunder and rain. A5 has 24 elements. Of order 5. Elements of order 3 and 15 elements of order 2. Actually, the solution to this one is available at the end of the text itself. So from there itself I am writing this thing. Cycle decomposition in your group A5 shows that any non-identity element in A5 is a 5-cycle or a 3-cycle or a product of two disjoint 2 cycles. Okay, and you can of course see that because these are the only types of elements available in your A5, and you can see that 5 cycles of course have order 5, all of them. Any 3 cycle has order 3, and any product of 2 disjoint 2 cycles has order 2, because LCM of 2 and 2 is 2. So you just have to find the number of such elements. Now the number of 5 cycles is of course the number of cyclic permutations of 5 simples, that is 5 minus 1 factorial. So there are 24 5 cycles in A5, and as such 24 elements of order 5. here. 20 elements of order 3, just like that you have to find the number of 3 cycles, and you also have to find the number of elements of this form, each of which is a product of 2 disjoint 2 cycles. So that part is already there in the answers, you can see that, and you will just get these figures. So this also I am just leaving here itself. So let's just see one more. In this one, we have to find a cyclic subgroup of A8, alternating group of degree 8 of order 4. Now, immediately when we think of order 4, we think of a 4 cycle. However, a single 4 cycle, of course, will generate a cyclic subgroup, but a 4 cycle is not an element in A8. It's not an even permutation. 4 is even, so the cycle is an odd permutation. To salvage the situation, you can of course consider this. Since the element this, which is a product of 2 4 cycles. Do you see the trick here? Because we are taking 2 4 cycles which are disjoint, the order of this permutation will be the LCM of 4 and 4, which is 4. So we are getting an element of order 4 in S8, the large group S8. However, because this is an odd permutation and this is also an odd permutation, their product is even. So this belongs to A8. Since this element has order 4, the cyclic subgroup generated by this element will be a subgroup of order 4 in A8. Completes the solution, and let's just end the video here itself. We will solve more problems in the next Gallian update, and tomorrow of course we have our usual real analysis. So if you want to say something about these things, you can write in the comment section below, or you can mail me at my usual address. I will leave the link in the description. So given how much things are chaotic outside, so let me not just drag it anymore. So see you tomorrow with real analysis. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.